Okay, well, I'd like to start by thanking Oliver and Maria and Laura and Liam for the opportunity to speak. It's great to be here. And I should also mention before we get started that this is all joint work with Foster Tom, who's also in the audience. And so he can handle any of the really hard questions. So the basic idea here is we're going to be studying the chromatic symmetric function. But the major thing I want you to take away is that sometimes if you want to know something about the expansion of this function in a particular basis, it's actually better to start in another basis where you can understand things better and then change basis. So what we're going to do is we're interested primarily in the 3+1 free conjecture, which is about an expansion in the elementary basis. But we're going to start off in the monomial basis where we have more control and then do a basis change. And that way we'll be able to get a nice result, as you'll see. And in fact, several nice results. I'm only going to show you one of our results in this talk in any detail. And then I'll end with some comments. So let's get started. Oh, and I should also say, unfortunately, my computer's set up so that I cannot see the chat. So if you've got a question at any point, just unmute yourself and I'll be happy to clarify. Okay, so let's first of all talk about, now I'm not assuming that people are familiar with the chromatic symmetric function, so I'm going to build that up from the ground. Those of you who are experts, I apologize. You can take the next 5 minutes to do something else if you wish, and I won't take it amiss. So we've got a graph, G, with vertices V and edges E. And P is going to be the positive integers. And then I've got a set of variables, boldface X, indexed by those positive integers. So now for any function from the vertex set to the positive integers, which you should think of as a coloring, you can associate with that a monomial in the following very easy way. You just take for each color that appears in your coloring, you just take X sub that color as a factor in your monomial X to the C. And of course, we're primarily interested in what are called proper colorings. That is the coloring such that if I have an edge from U to V, then its endpoints have different colors. So then Stanley's chromatic symmetric function, X of G, or if I want to be more precise, X of G boldface X, is just the generating function for all proper colorings. Just sum all these monomials over all possible proper colorings. And let's do a quick example to make absolutely sure that this is clear, since this is the focus of the talk. So let's take this path on 3 vertices, and we're going to compute X of G. Okay, well, let's start really simple. What if we only had 2 colors, say the colors 1 and 2? What could we do? Well, one possibility would be to put the colors 1 at the endpoints and the color 2 in the middle. That would give us the monomial x1 squared, right? From the 2 colors 1 here, x1 times x1, and then an x2 for the center. Or you could do it the other way around, right? You could put the 1 color in the center, and then the 2 endpoints have color 2. That would give me a monomial x1 and then x2 squared. And notice this is already looking symmetric. If I exchange the variables x1 and x2, this part of the function remains invariant. Okay, well, let's continue on our merry way then. What if I use the colors 1 and 3? Well, it's a similar story, right? You could put the 1s at the endpoints and the 3 in the middle, or the 3 at the endpoints and the 1 in the middle. That's going to give you x1 squared x3 and x1 x3 squared. And hopefully it should be pretty clear that no matter which 2 colors you pick, you're always, right, if they're colors I and J, you're always going to get an xi squared xj plus xi xj squared, right? So you're going to get every possible monomial of that type, nice and symmetric. But that's, of course, not the only way we could color this path. We could color it with 3 different colors. Suppose we use the colors 1, 2, and 3. Well, since we have 3 distinct colors and 3 vertices, any way I put those colors on the vertices is going to be a proper coloring. So we've got 3 vertices to assign 3 colors in a bijective way. That's 3 factorial ways of doing it. So you're going to get 6, say if I use the colors 1, 2, and 3, x1, x2, x3. And again, it doesn't matter that we picked the colors 1, 2, and 3. We could have picked the colors 1, 5, and 7, or 2 billion, 5 million, et cetera, et cetera. Okay? Questions about this? So this is the chromatic symmetric function. Okay, I see heads nodding in the preferred direction. So let's go on then. So, right, general definition, a power series F in these variables X is symmetric if it's invariant under a permutation of variables. And it's easy to see that this chromatic symmetric function is indeed symmetric for any graph, because think about it. What does permuting the variables mean? Permuting the variables just means permuting the colors. But if I permute the colors in a proper coloring, it stays proper, right? So this will always stay symmetric. And then bases for the algebra sim X of symmetric functions in X are indexed by partitions. So let me do a brief review of some basic definitions of partitions. So a partition of a non-negative integer n is just a way of writing n as a sum of certain positive integers called parts. These lambda I are called parts. And since we don't care which order they really come in, we usually put them in a canonical weakly decreasing order. Okay. So for example, one partition of 10 would be 4, 3, 3, right? 4 plus 3 plus 3 gives me 10, and I've put them in weakly decreasing order. Now, we're going to use the Young diagram of lambda. So this is a diagram of boxes, but we're not going to do it in the same way as in Sylvie's talk. We're going to use English notation. So the boxes are going to be in rows. The ith row will have lambda I boxes, and they're all left justified. So write 4 boxes in the first row, 3 in the next, and 3 in the next. Okay. And from this, we can get the transpose of lambda, which I'll denote by, whoopsie, lambda super t with parts lambda super t1, lambda super t2, etc. And you just take this Young diagram, transpose it across this main diagonal here. So rows become columns and columns become rows. So for example, in this here, right, this column would become the first row, length 3, and similarly 3, 3, 3, 1. Okay, so that's basics about partitions. We're also going to need some basic stuff about some fundamental invariants that come from graph theory. So let's take a look at those. So suppose I've got a graph, and suppose I take a subset of vertices, I. We'll say that I is independent if whenever I pick 2 vertices from I, there's never an edge between them. Okay, so let's take a look at this graph. Here's an independent set, right? If I take U and W, there's only 2 vertices, so I only have to check, is there an edge between them? No, there's not. Now, why would we care about independent sets? Well, think about it. Suppose I take a proper coloring and look at all the vertices that are colored a given color, say color I, right? So the inverse image of I under the coloring. That's an independent set, right? Because it's a proper coloring. If you've got a proper coloring, you're not allowed to have 2 things of the same color with an edge between them. So this is a natural thing to be looking at in this context. And in particular, we're going to need the independence number of G, classical invariant, alpha of G, which is just the maximum number of elements in an independent set of G. So for example, in this graph, alpha of G is 2, right? I've already shown you an independent set with 2 elements, and you can't do any better than that. Why not? Well, we've got this triangle here where everything is adjacent. So if I want an independent set, I can pick at most 1 vertex from this triangle, and then I can pick W as well. So this is indeed a maximum. At the other end of the spectrum are what are called cliques or complete subgraphs. So a subset of vertices C is a clique if whenever you pick 2 vertices in C, you always have an edge there. Okay. So as we just pointed out, UVX here is a clique. And then there's the corresponding clique number, omega of G, which is the maximum number of elements in a clique. And it's pretty clear that in this graph, omega of G is 3, because here's a clique with 3 vertices. And if I take all 4 vertices, well, that's not a complete graph on 4 vertices. Okay, so alpha of G, first letter of the Greek alphabet, no edges. Omega of G, last letter of the Greek alphabet, all edges. Keep those straight because we're going to need them. Any questions about alpha and omega? Good. So, as I said, we're going to start with the monomial symmetric functions. So what are they? Well, m sub lambda, you just take all the monomials in your variables that have exponent partition lambda, right? The exponents are a sequence of positive integers, put them in non-increasing order, that gives you a partition. So for example, m21 would be the sum of all things with a square and a first power. It's like x1 squared, x2, x1, x2, x squared, et cetera, et cetera. So, crucial definition for us. Suppose I've got any basis for the symmetric functions. I take a function and expand it in that basis. Then we'll say that b sub mu appears in f of x if the coefficient, right, these c lambdas are the coefficients in the expansion, if the coefficient of this b mu is non-zero. Now notice we're not saying that it's positive or negative. We're just saying that it's not 0. So here's a lemma for the theorem that we're trying to prove. Suppose we're given a particular lambda, and suppose we know that m lambda appears in x of g. Then alpha of g, the independence number, is bounded below by the length of the first row of lambda, and omega of g is bounded above by the length of the first column. Now, this is really easy to prove, so let me show you the proof of at least A. Because think about it. If m lambda appears in x of g, then in particular, the monomial x1 to the lambda 1, x2 to the lambda 2 appears with non-zero coefficient. But what does this tell you? This is telling you that there's some proper coloring of g where we've got lambda 1 vertices of color 1. But those vertices have got to be independent, right? From what we talked about before. So we've got an independent set of size lambda 1. And remember, alpha of g is the maximum size of an independent set. So alpha of g is at least the size of that independent set that we just found. Okay, so very easy, very quick, no problems. Any questions before we go over to the elementaries? Okay. Well, what are the elementaries? Let me remind you, if you haven't seen them before, I know a good book I could recommend for you to find out more about symmetric functions. In any event, E sub n is just the sum of all the monomials which are square free of degree n. So just n single powers. And then to get E lambda for a partition, you just multiply E lambda 1, E lambda 2, et cetera, where these E sub lambda i's are defined by the previous part of the definition. So for example, E sub 3, just the sum of all products of 3 singleton powers, x1, x2, x3, et cetera. And then E4, 3, 3, you take E4 times E3 times E3, where E3 is given here, and E4 is the same thing, only you have 4 things in each factor. So here's something which we're calling the alpha omega theorem. So now take x of g and expand it in the E basis. Then omega of g is at most the size of the first row, and alpha of g is at least the size of the first column. And notice alpha and omega have switched from what we were talking about in the monomial basis. Well, how are we going to do this? In the obvious way, we're going to do a change of basis. If I want to express the m's in terms of the e's, it turns out that the coefficients that we get, the only non-zero coefficients we get, are for lambdas which are greater than or equal to mu transpose, where this greater than or equal to is lexicographic order. So just like words, right? You compare the first elements of both word, then the second elements. You find the first place where they differ, and then the one that has got the bigger element in it is the one which wins. But think about it. So by what we just showed, we want E lambda to appear. If E lambda is going to appear with non-zero coefficient, then there must be some mu in there which gave us such an E lambda. That is to say, mu transpose, just writing this inequality and the other way around, has got to be less than or equal to lambda. And now use what we just proved, right? From the previous proposition, omega of G was bounded above by mu transpose 1. And if this inequality holds, then in particular, the first parts bear this relation. End of story. So as I said, the purpose of this was to try and make some progress on the 3+1 free conjecture. So let me show you how we can do that. So just some notation, brackets mn is going to be the interval of integers from m to n. And if m is 1, we just say brackets n for the interval from 1 to n. And then a natural unit interval graph G is defined as follows. The vertex set has got to be the numbers from 1 to n. So that means in particular, if I've got an edge, I can compare the sizes of the two endpoints. So if I've got an edge between I and j, where I'm going to write the edge in the form where I is smaller than j, if that's an edge, that implies that the whole interval from I to j must be a clique. Okay. And I should also say that I'm not going to be there are other types of interval graphs. I'm not going to be talking about them in this lecture, so I'm just going to say interval graph from now on. Again, let's see what this means. This graph here is an interval graph. Why? Well, think about it. It has the edge 1, 3, and that should imply that all the edges between vertices between 1 and 3 should be present, and they are. 1, 2 is present, and 2, 3 is present. This is not an interval graph, right? Because I've got the edge 1, 4, but that would imply that all the edges between vertices between 1 and 4 should be present, but 1, 3 is not present and 2, 4 was not present, right? If this were an interval graph, it would give you a clique of size 4. So we now want to talk about positivity. So suppose I take my f of x and expand in my basis b lambda. We'll say that function is b positive if each b mu which appears in f of x does so with positive coefficient. And then this famous conjecture of Stanley and Stembridge, which was refined by Mathieu Guy-Paquet, is that if G is an interval graph, then x of G is E positive. And this is a necessary condition. There are definitely graphs whose expansions are not E positive. So here's an example of one of the things that we can do to push at least a little bit closer to proving this conjecture. Suppose we have an interval graph, and suppose we have any lambda with lambda 1 at most 3, right? So lambda has at most 3 columns. Then the coefficient of E lambda in x of G is non-negative. Now there's something I want to point out here because this is another important overall or overarching point of the lecture. Most of the work on this conjecture that has been done up to this point has been of the form, take some subset of the interval graphs, some naturally defined subset, and show that at least those graphs are E positive. We can use this technique to turn that on its head. Rather than looking at a subset of graphs and looking at all their coefficients, we can take a specific type of coefficient, right? In this case, the E lambdas where lambda 1 is at most 3, and show that that's got to be non-negative in all interval graphs. So it's kind of reversing the viewpoint. And this is actually going to be simple to prove because the hard work has been done by somebody else. So if E lambda appears in x of G by the alpha omega theorem, that says that omega of G, the size of the largest clique, is at most 3. That is a very, right? That's a very severe restriction. That means you can't have any K4s, K5s. The biggest complete graph you can have is if it's got 3 vertices. And in particular, since this is an interval graph, that's saying if I take any edge, the difference between the sizes of the 2 endpoints is at most 2, right? It can't be 3 or more, right? Look here, this has difference 3, but it's not an interval graph because if it were, it would imply a K4. But Samantha Dahlberg has shown that these particular interval graphs satisfying this particular property are in fact D-positive. So not only are their coefficients with lambda 1 less than or equal to 3 positive or non-negative, they're all non-negative. So basically the way you could think about this is saying that in these graphs, which Dahlberg considered, they're non-negative, and in every other graph, they're 0. They do not appear at all. Okay, so comments to end. There are a bunch of other results. I don't have time to tell you all of them, but let me just mention a few of the others that you can get using this technique. First of all, we have a strengthening of the alpha omega theorem using basically what people today call a Green's invariant. Those of you not familiar with Green's invariant, it's rather than just looking at the length of the first row or the length of the first column, you look at the sum of the first lengths of the first k rows or the sum of the lengths of the first k columns. And you can say something in that case about independent sets and cliques. And you can get a bunch of results for other shapes. Let me just show you a canonical one of the ones that we can get. Again, we've got look at an interval graph and look at the E lambdas where lambda is of the following form. Lambda starts with a partition mu, which can be a partition of any number up through 10. Pick your favorite partition of a number, which is at most 10. And then after that, add as many ones as you like. So just extend the first column as long as you want. Those coefficients are also always non-negative. Now, of course, one obvious thing to think about is, well, why just go via the M basis? There are lots of other nice bases out there. Let's use some of them, and you can get nice results. Let me show you a few of them. So suppose we go via the Schur basis. So from Stanley's fundamental paper where he introduced these chromatic symmetric functions, he proved this very beautiful result, which as a corollary says that the coefficient of En in X of G has this beautiful combinatorial interpretation. It's the number of acyclic orientations of G with a single sink. And therefore, in particular, it's non-negative, right? Because it counts something. So this is true in any graph, right? So in any graph, the coefficient of En is non-negative. Not necessary some of the other coefficients. We now, by going via the Schur basis, so the coefficients of the Schur basis have a nice explicit combinatorial interpretation given by Vesco-Gashadov in terms of certain things called p-tableau, where p here is a partially ordered set. And we can use this to give a very nice interpretation of the coefficient of En in terms of p-tableau. We should also mention that we're not the only people who have been using these basis change ideas to their advantage. So I should mention some of the other people in the literature that have been doing this. Cho and Ha proved, so there's a Q analog of the interval graph conjecture due to Shureshian and Wax, where Q keeps track of certain things in the graph called ascents. And they were able to prove this more general conjecture for graphs which are associated with posets of height at most 2. And their basic idea is to do this transition first to the Schurs and then to the E's, and then do some cancellation, fixed point free involution, not so fixed point free, just sign reversing involutions. Cho and Hung then proved the original conjecture for P of height 3, And most recently, Shiyun Wang has used the inverse Koska matrix to make more progress in Hi3, but now for an arbitrary key. And thanks so much for listening.
Great, let's thank Bruce. And I'll take some questions. Again, you can either unmute yourself to ask your question or post your question in the chat.
Yeah, I'll stop the share so I can see the chat.
Well, I can also read the chat to everyone.
Oh, okay.
Questions for Bruce?
I see. So I see some things about the power sum basis. And actually, Foster, do you want to, or you may already have, because you use that for your forest triples, right?
Oh, yeah, so I guess I've been working on something separate where I use an expansion in the power sum basis and convert P's to E's. This question in the chat was about using triangularity to talk about which partitions appear. And I don't think we quite have a similar result because there isn't quite the same triangularity between M's and P's. In fact, P1 to the N and Pn both often appear. Yeah, so I guess this is the discussion we were having here.
Okay.
So I have a question for you, Bruce. Can you talk a little more about what you get from these other green invariants?
Yeah, so basically the way it works is as follows. You rather than, so the, let's say alpha tells you the maximum size of a single independent set in your graph. Now look at all sets of vertices that can be written as a union of two independent sets in your graph. Take the maximum of that size. That is bounded by lambda 1 plus lambda 2. That's
I see. And so you get a corresponding result in the E basis as well.
Yes. So you essentially look at set partitions of your graph such that each block of the partition is either independent or a clique. That's the way you make the transition.
That's great. Great. Vishal, do you want to ask your question?
Yeah. So my question is, so if I have a fixed lambda and a fixed graph G, how hard is it to decide if M lambda is if M lambda is, the coefficient of M lambda is strictly positive, or if the coefficient of E lambda is strictly positive?
Okay.
Just
M lambda, it's always positive. There's an
no, but strictly positive.
Oh, strictly, I see. So not zero.
Yeah.
And hard, it depends upon, I mean, if you want to do it technically in terms of, are we talking NP complete? Well, it's probably polynomial. Well, it's not clear to me. I don't know enough about the computer science ways of talking about hard to be able to tell you exactly. But my suggestion would be to look at the literature and just see how hard is it to compute alpha. I'm sure graph theorists have thought about that, because like I said, alpha is one of the, when I teach graph theory 101, it's one of the first invariants I give. So that's got to be out there somewhere. And if alpha turns out to be hard, then of course this is indicating at least that the M's would be hard as well.
Right. Yeah, I would guess it is hard.
That's my feeling. As you said, as you saw, my initial gut reaction was that, and then I backed off because I didn't want to say something that I would regret later.
If you're talking about general graphs, it's NP hard.
It is NP hard. Okay, thanks.
Yeah. Can I sneak in a question here?
Absolutely.
Cool. Were you done, Vishal?
I have a slightly unrelated question, but maybe I'll ask it later at one of the interaction sessions.
Okay, maybe I can interrupt with a question related to your question and Oliver's question, if that's okay.
Great.
So I was curious if, so in your results, you're relying on just sort of knowing this, like the independence number, or like the alpha or the omega, right? But what if you had more explicit information related to those numbers? For example, you were working with a family of graphs where you actually knew and could enumerate all of the maximum independent sets. Would you be able to push your results further, you think?
You would certainly be able to say you would be able to say something about the number of non-zero coefficients if you were given that sort of information.
Interesting.
Yeah.
Cool. All right, thanks.
No problem.
I think also Maria and Vishal, I just interrupted. I'm sorry. Continue with
No problem.
the order of
Hey,
questions.
I'm glad that people are excited enough to have lots of questions.